Hey students, hope you had a good day. The next thing we're going to talk about is properties of parallelograms. So we have to remind ourselves, what is a parallelogram? Well, a parallelogram is a quadrilateral that has two pairs of parallel sides, and that can take many forms, but this is an example. We denote parallel sides by little arrows. One arrow, that means line segment AB and line segment DC are both parallel. And two arrows means that line segment AD and line segment BC are both parallel. That's what a parallelogram is. Properties of parallelograms. This is the properties of parallelogram theorem. There's 3 points. I've outlined them here. A, in any parallelogram, opposite sides are congruent. So in this parallelogram here that we'll use in a minute, we have to say that opposite sides are congruent. So we know AB, line segment AB is congruent to line segment DC, and we want to check and see if line segment AD is congruent to BC. And so this is what we're going to prove here. But if we reference the properties of parallelogram theorem, we can just reference that theorem, and that proves it for us without having to do this whole other proof. The second thing the properties of parallelogram theorem says is that opposite angles are congruent. Opposite angles are congruent. So this angle, ABC, is an opposite angle to angle ADC. This angle and this angle are opposite angles, and they're congruent. And the third thing that the properties of parallelograms theorem says is that the diagonals intersect at their midpoint. Intersect at their midpoint. So in a given parallelograms are actually pretty easy to draw. Diagonal, they intersect at midpoints. That means each of these segments away from this intersection point is even. And these things will be self-evident in a minute. So these are the 3 points of the properties of parallelogram theorem. Let's go ahead and prove this. So we have a given statement that says I have a parallelogram ABCD, and I've already pre-drawn that for us. The things we're trying to prove is the opposite sides are congruent. AB and DC, or CD as it's written here, AD and CB. So these ones and these ones. That's what we're trying to prove. So that is point A of the properties of parallelogram theorem, and we might uncover some others along the way. Okay, so the first thing, we're going to bring back an old concept, and this would be a difficult one to do from scratch for you students, but it's a helpful thing to think about. We're going to draw what's called an auxiliary line. Auxiliary means helper, a helper line. So I'm going to draw a helper line. And then once I have that helper line, I'm just going to label some angle names. Angle 1 is over here, angle 2. These are just names. They don't denote angle measurement or anything. So that is our auxiliary helper line, AC. And now you'll see that I have essentially 2 triangles back to back. 2 triangles back to back. Okay, so we have triangle ADC, and I have triangle CBA. CBA and ADC. So let's think about, well, we're told we have parallelograms, so I can definitely mark that these are parallel, and I've already done that from earlier in the video. So parallel lines is an interesting concept and one that we can really use to our advantage here. So I'm going to go ahead and say I'm going to use that advantage. So let's write our givens first. Let's say I have parallelogram A, B, C, D. This is given. Our next thing we might want to prove is if I keep in mind these triangles, I've got to start proving some stuff about these triangles. So I might try and prove that these triangles are congruent. If I can prove that, then I can prove that their edges are congruent through CPCF. So I'm going to focus on these angles, and you might have come to that thought already. So if I can prove that angle 2 is congruent to angle 4, how might I prove that? Angle 2 is congruent to angle 4. And I prove this with the parallel lines imply alternate interior angle congruency theorem. And I'm just going to reference, you wouldn't really have to do this, but I'm going to really reference line segment AD is parallel to line segment BC. AD and BC, so this is an alternate interior angle. And I could do the same thing using line segment AB and line segment DC. Of course, this is going to be different angles. Parallel lines imply alternate interior angle congruency. Which angles is that going to be? I'm talking about this line and this line. Well, 1 and 3. Angle 1 is congruent to angle 3. Okay, so now I've got this one's here, double arc, single arc, just to note how they follow. I've got angle, 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 angle. Well, if I could figure out that this side was even on both triangles, then I could really make some headway. Well, luckily I can. So you might have already thought that. Line segment AC is congruent to itself, and you should immediately in your head be shouting out, or at your house be shouting out. This is because of the reflexive property of congruence. Perfect. So now that I have that, I've got angle, side, angle, angle, side, angle. That works. So I can say triangle ADC is congruent to triangle CBA. And I can reference the angle, side, angle, triangle congruency theorem. Remember, I only need 3 pieces of information to prove that all 6 are congruent. So all 6 pieces are congruent. I can go ahead and take care of these 2 proof statements. AB is congruent to line segment CD, and AD is congruent, line segment AD is congruent to line segment CB. How might I prove that, both of these things? Well, through CPCF, as we talked about before. Awesome. Another cool part about properties of parallelograms is we've got a unique result of the properties of parallelograms theorem is if I've got 2 sides, 2 opposite sides that are congruent, then I can envision, let's say I'm going to look at this side right here and this side over here. I'm going to envision those as just parallel lines these opposite sides. I'm going to just envision as going on forever, being parallel lines. And I could envision I could drop down a vertical. This is a helper line. That's going to be equal, that's going to be equal. So these 2 triangles are going to be 2 angle side angle triangles, or I could call them hypotenuse leg or whatever I wanted to do. Angle side angle might work the best. But if this is, let's say, x, and this is x, then This is a cool result. This says that the distance between parallel lines is always constant. That's pretty unique and cool. Before we kind of knew that, but we couldn't really prove it. So we would just have to say parallel lines never intersect. That's the definition of parallel lines. Now we can say that the distance between parallel lines is always constant. Another cool thing about parallel lines is that they are twofold rotation symmetric. So here I've cut out a parallelogram out of a playing card. We're going to examine this rotation symmetry. Notice this parallelogram is rather close to a rhombus, but it could work with any parallelogram. I hope you see why. So it's not only twofold rotation symmetric, it's twofold rotation symmetric about the intersection of its diagonals. I can't even spell right now. Not intersection. Diagonals. So let's check this out. Let's call this first little cherub put a little A next to him. His name is Alva. So just so you can keep track of him. So I'm going to turn this. Is this rotation symmetry yet? No. It's got to coincide with the original which I've traced. Here it is, once. That's one point where it's rotation symmetric, and then I can do it again. Twofold rotation symmetry. That's another cool result. Okay, be ready tomorrow to know how many fold rotation symmetry a parallelogram has. Know the corollary, which says that the distance between parallel lines is always constant. And you should have these memorized in the properties of parallelograms theorem. That's A, B, C. Opposite sides are congruent, opposite angles are congruent, and the diagonals intersect at their midpoint. I'd recommend taking these notes, and then you will be prepared. Hint, hint. Have a good one.